Huh?
Uh-huh.
Now I gotta get all this stuff back up here. Let's do that. Everybody see that? It's a bit slow. Okay, just finishing up from last time. Last time I got confused. I said something silly. I just want to correct. I was talking about Hess's law. I said, you know, say you have this reaction and the enthalpy change is delta H1, and you have this one, it's delta H2. So then I said you can take the difference of the two reactions, and delta H3 would be 2 delta H1 minus delta H2, called Hess's law. You can treat chemical reactions like algebraic equations, like you think of lead, oxygen as algebraic variables, x plus 1/2 y equals z. You think of this as a plus y equals b, then 2 times x plus b equals, you just subtract them like algebraic equations. Then I said if under the convention, there's a convention, this always works where delta is the change in heat, delta is the change in heat going products minus reactants. If you have the convention, which is purely a convention, that elements, pure elements at 298 degrees, their enthalpy is 0, then you can also write at 298 Kelvin, you can just talk about absolute enthalpies because the enthalpies of the elements. Then I said the same thing holds for any extensive property, and then I got confused. Yeah, it does, of course. You can replace H by U or V, so if you replace that by U, then delta U3 is 2 delta U1 minus delta U2. If they're entropy, then delta S1. Delta S3 equals 2 delta S1 minus delta S2, and so on. Volume works for everything. This only works for H because you only have the convention. We do not have the convention that say U or V or whatever is 0 at 298 kelvins for elements. Okay, so you can't talk about absolute, but you can always talk about the difference for the same reason. Okay, so delta G3 is 2 delta G1 minus delta G2 with this treatment like algebraic equations. All right. So for the devoir homework problems, I assigned these numbers here. I put the answers up on the website, which I presume you've all looked at and looked over. And so I will ask, do you have any problems? Do you want me to talk about these? I have you also have now the answers for them. Those are the answers which you found on the website. Okay, if you've looked them over and you understand it, then fine. If you would like me to discuss something, please let me know. So number 1, anybody? Questions? Number 2. Okay, anything in series 1. 1, 2, 3, 4, 5, 6 of series 1. Does anybody? Don't be shy. If you've had a problem, you didn't understand it, you couldn't get the answer, even after looking at the answer on the website. I really prefer that you look at the answer on the website before you come here so that we save time. If that clears things up for you, then we all save time. Anything on series 1? Anything I want to tell you about series 1? No. Number 3 was the drop calorimeter, but we talked all about the drop calorimeter before. Number 4 was the, no, I looked at the wrong number there, sorry. I looked at the wrong thing. Number 3 was the bottle which is full of air, 4 degrees. So we talked about the, let's put on number 3. I mean, you may have got the answer, but I just want to talk about a few. Number 3, you have a bottle, closed bottle is full of air at 40 degrees. The bottle is cooled slowly. You observe water starts to condense on the outside at 25 degrees Celsius. 25 degrees Celsius then is called the dew point, right? The point de rosée. That's the point, the temperature at which you start to get condensation. You heat the bottle back up to 30 degrees Celsius. All the water is now in the vapor state, and you pass it over. You pass it with dry argon over a moat which contains P2O5. The P2O5 absorbs all the water. You weigh the P2O5 before and after, and that tells you how much water was in the container. Okay, from that you can calculate the vapor pressure, but what the tension de vapeur, the vapor pressure, but what is the definition of vapor pressure? This here. What is the definition of vapor pressure? What is vapor pressure? We talk about the partial pressure of a gas, we talk about the vapor pressure, what's the difference?
Partial pressure and vapor pressure.
Okay, in this room there's water vapor.
Yes.
And the partial pressure is the pressure of that water vapor if it alone occupied the room. So if this room, if it's an ideal gas, if this has 1% water vapor, then the partial pressure of water vapor is 0.01 atmospheres, approximately. That's the partial pressure. It's just the pressure of the gas if it alone occupied the volume. The sum of the partial pressures equals the total pressure. So if you consider the partial pressure of oxygen plus nitrogen plus CO2 plus water plus everything else that's here, the sum will be the total pressure. Is that always true?
Closed system. Not closed system.
Well, that's close. Let's assume it's a closed system. Some of the, I mean, it seems obvious when just from the word that the sum of the partial pressures, the sum of the parts is the whole. But no, that's not true. Always not in that case. Partial pressure is badly named. It is not. Okay. The reason being, if they're ideal gases, yes. That's called Dalton's, that's part of Dalton's law. If you have ideal gases, the sum of the oxygen and the nitrogen. So if the oxygen in this room if the oxygen in this room were all alone, it would have a pressure of 0.21. If the nitrogen were all alone, it would have a pressure of 0.79. Okay, but if you put the two together, okay, remember ideal gases don't interact. So if you put them together and they're ideal gases, then the total pressure is 1.00. But if they do interact, then putting them together causes some interaction and the total pressure could be different from 1 atmosphere, very slightly. Okay, but Dalton's law is not. The sum of the partial pressures equals the total pressure in the case of ideal gases. You should not think of, if you want to be exact, the partial pressure is not the part of the pressure due to oxygen. It's the pressure that oxygen would have if it alone occupied. Okay, but for all intents and purposes in this course, we're talking about ideal gases. I'm not going to, in this course, talk about non-ideal gases. That's not really our job, but if you're dealing with gases that are far from ideal, then you have to realize the difference between the partial pressure and this. Vapor pressure, though, what's the vapor pressure? So if the total pressure of water vapor in this room is 0.01, is that the vapor pressure of water? The vapor pressure is what, by definition?
At equilibrium, the amount of, if we keep a material, how much amount will be present in the vapor phase and how much will be stored?
Well, how much amount, how much pressure? It's the partial pressure in equilibrium with the liquid. Okay, so if you have a container, seal a container, up here we have H2O gas. If that's the only thing in the container, then the pressure of H2O is the partial pressure of H2O. If we have H2O liquid down here we have H2O liquid, and the system's in equilibrium, at a given temperature there will only be one partial pressure of water. If the partial pressure is higher, the gas will condense. If the partial pressure is lower, then that vapor, okay, so in equilibrium with the liquid, at any T there's only one partial pressure. The partial pressure in equilibrium with the liquid is called the vapor pressure of the liquid. Or you can have a gas in equilibrium with a solid, that's the vapor pressure of a solid for sublimation. So vapor pressure is the partial pressure in equilibrium with the liquid or with the gas. Okay, if there's two phases present, then there has to be only one. The partial pressure can be anything. The vapor pressure is the partial pressure in equilibrium with the liquid or solid.
Excuse me. You talked about vapor. Is there any difference between vapor and gas? Or
No. Okay, also the partial pressure, if you have a mixture of several gases, the partial pressure of oxygen is equal to the total pressure. times the mole fraction of oxygen in the gas phase. Okay, so the mole fraction of oxygen, okay, which is equal to the total pressure times, well, let's say in the air is 21% oxygen, so this would be 0.21 over 0.21 plus 0.79. Okay, mole fraction. Again, what are the assumptions here? When is this applicable? Ideal gas. Okay, that is called Dalton's law. The law of Dalton. It's only, again, true for ideal gases in which the molecules don't interact with each other. If there's interaction among the molecules, you get a small deviation, which will be greater as the pressure gets greater and the temperature gets lower. And from this, you can derive that the sum of the partial pressures equals the total pressure. There's two ways of saying the same thing. So you should then convince yourself that in question 3, read question 3 again in light of what you know about vapor pressure. Okay, and convince yourself that the partial, that in question 3, what you're measuring is the vapor pressure. Okay. If you don't understand it, then you can ask me on Thursday, how is it that number 3 gives me the vapor pressure? Okay. Question 4, did you understand question 4? Question 4, if you have no questions, I'm not going to answer them. Okay. Question 5 is maybe a little bit interesting because it shows something. Question 5. Okay. Question 5, we said, talked on Thursday about how in a bomb calorimeter you measure the internal energy change, delta U. Delta U is equal to the heat at constant volume, so you measure the heat at constant volume. So in a bomb calorimeter, we take the bomb, the big steel cylinder, we put in some iron carbide, a whole lot of oxygen, we put a spark in it somehow, the thing explodes, all the iron carbide's consumed, and you get Fe3O4 plus CO. And you measure the heat evolved, and that's equal to delta U. Okay, however, that's easy to measure, but so it's easy to measure a reaction at constant volume, but what we're really interested in is the enthalpy, the heat of a reaction at constant pressure, because that's more what goes on in reality. So from this, how do we calculate the heat of the reaction, delta H, at constant pressure? All right. So this is the calculation you do after you run your bomb calorimeter. You use the definition of H as U plus PV, and you say delta H is delta U plus delta PV. Okay, so we measure delta U. What is delta PV? Okay, well, the delta PV, first of all, this term is quite small relative to this term. So it's okay if we make some assumptions, because there are assumptions in a second order term anyway. The volume of the solids is very small. Here you have, these are solids, the oxygen and CO2 are gases. The volume of the gases is much greater than the volume of the solids. Okay, so in terms of the volume change, or the change in pressure is really due to the change in the number of moles of gases, not due to the change in the volume of the solids, which can assume to be negligible. On the left you have 3 moles of oxygen, and on the right you have 1 mole of CO2. So you start out in this container with 3 moles of oxygen, and after you're done you have 1 mole of CO2. So the number of moles of gas has decreased, so the pressure has gone down. And that's where the PV term comes from mainly. Delta PV is delta nRT, assuming the gases are ideal. And okay, PV is nRT, so the change in PV is the change in nRT. This is an isothermal reaction, so T is constant, so it's RT times delta N, the change in number of moles, which is -2. Okay, so delta H is delta U minus 2 RT. So we see the difference is 1180 or 4940 joules, about 5 kilojoules, out of a total delta U of, so delta U is 1140 kilojoules. What the hell am I doing? Okay, with delta U is 1180, the difference was about 25, so it's about 5, sorry. So it's a very small. Okay, so 1140 was changed to 1145, which is not negligible, but the correction is easily made now. There's temperature's not exactly constant, the volume of the solids isn't exactly zero, the gases are not ideal because you're running at a pretty high pressure to be sure you've got a fast reaction, but those aren't going to make a significant difference within this. Rather than 5, it might be 4.9, but I mean 1140 is plus or minus 1 or 2 anyway, so that's how you make the correction. So that's how heats of reaction can be measured. You measure delta U in a bomb calorimeter, and then you make this correction for the change in the number of gas moles. No question about number 6. Question?
We have measured delta U at constant temperature. But we
Yeah,
can
well.
measure it at constant volume and go volume.
It's measured at constant volume, and for all intents and purposes, it's measured at constant temperature. Remember, you put the bomb inside the big calorimeter at 25 degrees, the bomb explodes, but after it's all done, the gas cools back down, transfers the heat to the inside the bomb. At the beginning, you have the reactants at 25 degrees. During the reaction, the temperature and pressure can change, but eventually all the heat is transferred back to the calorimeter, and when you end it up, they're cooled back down to 25 degrees again. You measure the total heat that was evolved. And since delta H is a state property, delta H is independent of the path. Series 2.
Excuse me, but the volume container is not constant.
It is constant, yes.
But the gas amount is changing.
The gas amount changes, but the volume, the container is a sealed container containing a fixed amount of material. The number of moles of gas will change because they're absorbed in the reaction.
So delta V is not zero.
So W is 0 because
Yeah,
there's no expansion. Nothing. The number of moles changes, but no work. There's no work being done. It's a sealed, closed container at a fixed volume.
So that's delta PV, not just V.
It's delta. Yeah, delta PV.
Yeah,
H is U plus PV. Actually, what I should be doing, Yeah, okay. Delta H is delta U plus delta PV. Right. Not P delta V, no. P delta V would be 0. It's delta PV. Or V delta P if you like. And that's okay. But I wrote it this way because it's easier. Yeah, V delta P is all right, but that's the same thing. Delta NRG. T's constant. To all intents and purposes, the T's constant. I think 2.1 is pretty straightforward. 2.2, drop calorimeter. Number 3 was the drop calorimeter. These are some actual logic here. 4, 5, 8, anything I want to talk about? No, 4 and 5 is, 4 is a traditional heat balance. Number 5, probably got the answer, but let's just talk about it. Number 5 was okay, calcination. What is calcination? Calcination is the decomposition of a carbonate. Not necessarily calcium. Carbonate could be strontium carbonate. Decomposition of a carbonate to form CO2, and the oxide is a calcination. So we're calcining limestone. Calcium carbonate is calcined to form CaO. Probably this is one of the most important reactions in technology. There's millions of tons of this stuff made. You charge limestone at 25 degrees into a furnace at 800 degrees where the calcination takes place. The products are calcium oxide and CO2. How much electrical energy is it necessary to produce 1,000 kilograms of CO? Ignore all losses by radiation and convection. Okay, so it's an endothermic reaction. That is, it requires heat. Where am I here? Okay, so the way I like to do this is as follows. You this is your final, your initial state is calcium carbonate, and your final state is CaO and CO at 298, and your final state is CaO and CO2 at 1073. Okay, lime and CO2. Okay, the total heat is 0. Remember, delta H is the energy exchange with the surroundings. Now I'm saying there's no losses by heat, there's no losses by convection, there's no exchange with the surroundings. We assume that the furnace doesn't lose much heat. In principle, actually it does. So the delta H will be slightly negative, but in this ideal adiabatic reaction, the total delta H for the reaction is 0, going from the initial to the final state. So what happens is this delta H here, there's a delta H 298, and then there's the delta H to heat the... Now, you can consider this is a hypothetical path, because in reality, you throw the limestone into the furnace at 298, and it doesn't all react immediately at 298, and then you heat the products. What happens is it decomposes as it's being heated. So you're heating the CaCO3, and it's decomposing as it's going up to 800 degrees. So the real path is very complex. But it doesn't matter because delta H is a state property. So delta H is simply H of the final state minus H of the initial state, totally independent of the path. So to do the problem, we propose a hypothetical path for which we can do the calculation. Okay, so we assume that CaCO3 dissociates at 298, and then we heat up the product, because these can be calculated. That's the only reason we do it. This isn't what really happens, but it's the same delta H. So the delta H at 298, so the total delta H is delta H 298 plus 1 plus 2, and the delta H total is 0. Delta H 298 is being given as 177,800. That's positive. It's an endothermic reaction. You have to supply energy to heat the stuff. Plus, you also have to supply energy to heat it up. Okay. Why do you want to heat it up? Simply because it's going to be too slow at 298. Actually, probably closer to the truth is you heat the CaCO3 almost to 800 degrees before it starts to react. Okay, so you heat this thing up to about 1073 and then it reacts. But for that, we don't have the data easily available at the table, so we do it this totally silly way. And then from 1073, for heating the products, is just the integral of sum of the CP's dt. You add the whole thing up, and you set it equal to 0. Then you can multiply by 1,000 kilograms and convert it to kilowatt hours. Okay, but this is how we draw the little cycle. Okay, so the two things here, the total H is the energy exchange with the surroundings at constant pressure, okay, and it's independent of the path, so it's equal to 0. If there are heat losses, then delta H would be negative, and a little bit you'd have to put that into the equation. And let's just look at number 8 as well, and then I'll be done with it. 8 is very similar. These are classical heat balances. Okay, the flame temperature of methane with an excess air. Okay, the flame temperature, this is the way chemists or chemical engineers use to compare various fuels. The flame temperature is the temperature that the flame would reach if there were no heat losses, if it were adiabatic. Okay, in that case, you're talking about an exothermic reaction. We could kind of go back to the previous one, actually. It's similar to the previous one. In the previous one here, we had this was a positive delta H, so you have to add heat. If this were negative, suppose this were negative, then you'd have a negative heat here, and the negative heat would then be used to heat up the products. So this could be a combustion with a negative heat, and it's equal to delta H1 plus delta H2. So the thing would reach a high temperature all by itself. And the temperature it would reach if delta H total were 0 would be called the flame temperature. Anyway, we'll do that for here. Okay, methane is burned with an excess, a stoichiometric quantity of air. That means after the reaction there's no air left, or methane, exactly the right amount just to burn it. That's called a stoichiometric amount of air. The combustion is complete.
Sorry, you're doing number 7.
I'm doing number 7. Oh, sorry, number 7 was some number 8. Okay, here we go. Methane is burned at 25 degrees centigrade with 5 times the stoichiometric quantity of air. So the stoichiometric quantity of air would be the amount required to burn the methane completely. 5 times means you got excess air. So you've got like a burner with methane coming in here and air coming in here, and you got way more air than you need to. Okay. Combustion is complete. That means there's no reactants left. That is, for each mole of CH4 which enters the burner, 10 moles of oxygen enter also, as they bring along with them a bunch of nitrogen because it's air. All the CH4 is consumed. The combustion is adiabatic, no heat loss. What is the temperature of the flame? Okay, so I give you a bunch of data here. All right, so that's number 8. Okay. So the way we do it is as follows. I write the reaction this way. Say this is the total reaction. So CH4, these are the reactants. CH4 plus 10 moles of oxygen, and this is the amount of nitrogen that comes in the air, 79/21 times 10. And you're left with CO2, 2 moles of H2O, 2 moles of oxygen have been used, and the nitrogen remains. The heat of that reaction at 298 is equal to this. The excess, the fact that there's excess air, nitrogen doesn't change the delta H. The delta H is just delta H. So now all that heat, this is like the previous reaction, that is negative heat, and you can consider that that is used to heat up the products. Once again, this is a hypothetical path. In actual fact, the methane is being heated as it's burned, and the path is very complicated, but it doesn't matter, delta H is constant. So this total heat, which is exothermic, is then used to heat up the products, and the total has to end up to be 0. So here I'm taking H minus H298. This is the heat required to heat 1 mole of CO2, 2 moles of water, 8 moles of oxygen, and 37 moles of nitrogen from T to T298 from the table. So I just add up the columns in the table. I make my own little table. This would be the amount at 1,000 degrees. This would be the amount at 900. This would be the amount at 800. Clearly, the 801 is somewhere in between here. I did a linear interpolation, and I end up with about 829 Kelvin. Okay, again, a heat balance. If there were heat losses, of course, if there are heat losses by radiation, convection, then the temperature will be lower. If you do not have excess oxygen, the temperature would be higher, because that's the whole point. You have to heat up. Most of this is lost. You have to heat up. All this oxygen and nitrogen are being heated. Okay, so it's much better. That's why it's much more efficient in your burner that you run it with exactly the stoichiometric amount. If you have too much fuel, then of course there's fuel left over, so A, you're wasting your fuel, and B, you have to heat up the excess fuel. If you use it with excess air, however, then you end up with excess air, and you're not getting the final temperature because you're wasting a lot of energy just heating up the excess air. Also, it's better to use pure oxygen, so if you use the right amount, exactly the right amount of air, you'll get a higher flame temperature than if you have excess air. If you use oxygen, you'll get a higher flame temperature than if you have air, because you don't have to heat up all that nitrogen. But that's how we do the heat balance. Any questions? Okay, so now I want to talk about, that was the first law of thermodynamics. The first law of thermodynamics is the conservation of energy, but there's more than that too. The first law of thermodynamics says that there's a difference, fundamental difference between heat and work. Heat being undirected random energy, work being directed energy. Okay, and remember that delta U is independent of the path, but delta U is equal to Q plus W, but Q and W are not independently path dependent. It's only their sum that's path independent. Okay, but now go to the second law of thermodynamics. Okay, the second law, there really are only 2 laws. You might talk about the third law. We can argue whether it's a law or not. Einstein said he thought that the second law of thermodynamics was the greatest triumph of the human mind ever. That's all. Of human reasoning was what he said. Okay, so the second law of thermodynamics talks about the direction of a spontaneous reaction. The first law tells you absolutely nothing about the direction of a reaction. Okay, if carbon plus oxygen burns to form CO2, we know that that's the spontaneous direction. Energy will be conserved, but if it went the other way, energy would also be conserved. It would give off heat, and the other way it would absorb heat. Okay, but the energy will be conserved no matter how you do it. If I drop something onto the table, this is obviously the spontaneous direction. And how does the energy balance work? Here we have potential energy. It's temporarily converted to kinetic energy, and when it hits the table, it's converted to heat. So there's heat in the table is equal to the potential energy. Now, this thing could automatically jump right up to my hand all by itself. And what would happen then is all the molecules in the table here vibrate just the right way to give it a force, bounces up to my hand, and the table would cool down a bit, and the heat energy lost by the table would be exactly equal to the heat. Okay, so first law will tell me nothing about which way the thing's going to fall. This clearly has to do with probability. As you know, it's very unlikely that all the molecules around here, which are vibrating randomly, are going to suddenly, by sheer chance, be vibrating in just the right way to give this thing a pump. But it's possible, but highly unlikely. I wouldn't wait around. If you have, it's also possible that all the molecules in this room they're moving randomly, and if they're moving randomly, why don't they all end up in that corner 1 second, and everything would be a vacuum and all. That's also possible, but this is very unlikely. Okay, simply because of probability. Okay, so the direction of things. So if we started off with all the air out there, and it was a vacuum, and we opened the hole, we would find that all the air rushed into the room. We don't find the air rushes out of the room. Okay, so but it would not violate the first law by any means. Energy was always going to be conserved. Or if we had, say, a container here with a hole between, and here we have oxygen, and here we have nitrogen, and we have a valve. We open the valve. What's going to happen is the oxygen and nitrogen are going to mix, and you're going to end up eventually with half a mole of oxygen, half a mole of nitrogen on either side. It's possible that if you had oxygen and nitrogen on both sides and you waited long enough, the oxygen would move one way, the nitrogen just by sheer chance, and they would separate themselves all by themselves, but it's unlikely. So it has to do with probability. The question then is, second law though, is we quantify this. We actually put a number to it, which is the triumph of the second law. The second law, by the way, depends, first of all, on there being a nature being microscopic and discrete. If we did not have atoms, molecules, there would be no second law. Okay, it really has to do with atoms and molecules. The probability of finding, if these were not atoms and molecules, if things were a continuum, you wouldn't really have heat and entropy. You could argue that you might in certain cases. But basically the second law depends upon there being a microscopic world with particles. Okay, even though the second law was discovered in 1830, way before anybody had the slightest idea about it, which was also quite amazing. The other thing is that the second law depends on there being a very large number of particles in any system. Okay, because as I said, the probability that this oxygen and nitrogen are suddenly going to separate simply because as they move around, just by chance, the oxygen happens to go this way and the nitrogen this way, and they separate. That only happens if there's a very they don't separate only if there's a very large number of molecules. If I had, say I have 4 oxygen molecules and over here I have 4 nitrogen molecules and they're all moving around, I'm sure if I wait a while I'm going to find that they mix or they separate, or let's put it this way, I start with 2 oxygens and 2 nitrogens on either side. Okay, and it's very likely after a few seconds I might find all the oxygens over here, then all the, okay, because there's only 4 atoms, but if you have 10 to the 23rd atoms, the probability that you would ever notice a detectable difference is 0. You'd never be able to measure that. Okay, so the second law depends upon macroscopic systems containing a large number of particles. When you're talking about a few particles, then the second law doesn't apply. Okay, so how do we quantify this? I'm not going to develop it. This was developed way back in 1830 by Clausius and the boys, and you can develop it that way, but this really makes it hard to understand what you're talking about in the modern context, so I'm going to develop it in the modern context. Then if I have time, I'll talk a little bit about the way they did it back then, simply because it's fascinating. Here we go, 42. Okay, so that the second law of thermodynamics, then we understand that the direction, the spontaneous direction of the process is somehow concerned with the probability, but how do we put a number to this? Okay, so here we are on the second law. Okay, the entropy of a system. So we define S, the entropy of a system, is an extensive state property. So it's an extensive property, so you have twice as many moles, you have twice as much entropy, which is given by Boltzmann's equation as follows. Boltzmann came up with his equation in about 1890. So Kb is a universal constant called Boltzmann's constant, and T is called the multiplicity of the system. The multiplicity of the system is the number of possible equivalent microstates in a macrostate. That is the number of quantum states for the system which are accessible under the applicable conditions of energy and so on. So for example, if you have a system can be described by a set of single particle energy levels, T is a number of ways of distributing the particles over the energy levels, keeping the total internal energy constant. What the hell does that mean? Let's do a very simple example. I'm not going to use quantum mechanics. I'll use classical mechanics, even though it doesn't really apply. Let's suppose you have a bunch of particles, some sort of a system, and this is the energy, and you have a number of quantum levels. And each quantum level has a quantum number, which we'll call 0, 1, 2, 3, 4, 5, 6. Now I'll even make life really, really simple. And I will say that the energy, this is the energy of each quantum level. So the energy quantum level, a particle in quantum level 0 has an energy 0. In quantum level 1, a particle has energy 1 unit, and so on. All right, so let us suppose that we have a system in which we have n is 5 particles. So let's say we have 5 particles. And we're going to put 5 particles into the system. I'm assuming classical mechanics, that is, we're not going to talk about Pauli's exclusion principle or anything. We just assume that everything can go. And we're assuming the particles are distinguishable, which isn't the case, but these are details. It doesn't make any difference to the final result. Let's suppose that E is 0. So that this is the total energy of, let's say U, sorry. U is 0. Internal energy of the system is 0. You have 5 particles. Clearly, all 5 particles have to be in the lowest energy level. In that case, what is the multiplicity of the system? The multiplicity of the system is 1. There's only one way of doing it. There's only one microstate. This is the macrostate. The macrostate is the energy of the system. The microstate is the number of ways that are equivalent to give you that energy. There's only one way to get an energy of 0, and that's to put all. This is the only microstate that gives you an energy of 0. Okay, so there's only one microstate. So the entropy of the system then is 0. Log 1 is 0. Okay, so this system has no disorder. It has a 0 entropy. Okay, let's suppose we heat it up a little bit. We make U equals to 1. U equal to 1. Okay, now classically there are 5 microstates. You could have 4 particles here and 1 particle here. Well, the particles now are distinguishable. Okay, so we're going to call them particles A, B, C, and D, and particle E could be up here. Or you could have particle E could be down here, and particle D could be up here. So on, so there are 5 ways. So there are 5 microstates, which give you exactly the same macrostate. All right, and now in this case, T equals 5, and the entropy is K log 5. So the entropy is positive. You can never have a negative entropy. When the system is perfectly ordered, you have an entropy of 0. Okay, let us suppose that the energy is equal to 2. In that case, there's various possibilities. You could have 4 zeros and a 2, and there's 5 ways you could do that. Or you could have 3 zeros and 2 1s. So 3 particles here and 2 particles here, or 4 particles here and 1 particle here, and then there's different ways of choosing the particles. So the number, the probability is going up. I'll let you work out for yourself. In that case, the T is 15. There are 15 microstates that will give you a total energy of 2. Okay? And so the entropy is going up. If you take the energy equals to 4, the number of microstates comes out to be 35. Okay, you could have 4 and a bunch of zeros. You could have a 3, a 1, and a bunch of zeros, 2 2s and zeros, in various ways. Okay, so the more particles you have, the higher the energy, meaning the higher the temperature. Okay, because the internal energy goes up with the temperature, the higher the multiplicity, and the higher the entropy of the system. Okay, so you eventually, if you have many particles and lots of energy levels at any temperature, you're going to get sort of a distribution that looks like this. This would be the number of particles at energy level I versus the energy level, and from knowing the energy levels and everything, you can work out the entropy of the system. And this is clearly so all microstates are equivalent, are equally probable. Okay, so the system that has the highest number of microstates is clearly the most probable system. Okay, so this is now a property, this is a state property of the system, is the entropy is a state property of the system. Okay, because if we know all the energy levels, we can work out what the most probable distribution is, and from the total distribution, from that we can work out the entropy of the system. And this is one way of actually measuring entropy, is using Boltzmann's equation. For gases, this is the best way of doing it. People measure the spectrum of gases, okay, with the spectrometer, and from the spectrum of gases you can actually see the energy levels, the distance between them. These are the vibrational, the rotational, the translational energy levels, and making a much more complicated thing because you have to take into account interactions, you got to take into account that the energy levels, where the energy levels are, that the things can interact with each other, you've got to take into account quantum effects, indistinguishability of the particles, but you can, and this is a whole thing called statistical mechanics, you can, from the energy levels of a gas at least, determine what the entropy is. And this is actually the most precise way, for at least for dilute gases, of obtaining the entropy of the system, and that's how it's done. This doesn't work for solids and liquids, it's just way too complicated. The interactions are this is assuming too that they're kind of independent. Okay, but in a real solid and liquid, if these are the vibrational energy levels in a solid, there's a tremendous amount of correlation between them, and if this is occupied and this is, okay, so you really cannot apply statistical mechanics, but in principle you can. Okay, and in principle then the entropy varies with k log t, so you can define it that way, and this will be a state property of the system. Okay. I'm going to show why I'm not going to talk about, we're not doing statistical mechanics to that level in this course. That's an entire subject of quantum mechanics, which is fascinating and very complicated. Okay, but you can actually, at least for simple systems like gases, you can measure the energy levels and you can actually calculate the entropy as a function of temperature. Entropy is related, just to show you a little bit more about it. I'm not trying to do this whole thing rigorously. I assume you've all seen entropy, but I'm trying to give you some ideas of what it all means. Information theory, which was developed in the late 1940s by Shannon and people. This is used in all communication theory nowadays, and they talk about entropy as well. So let's suppose, that gives you a few ideas. Let's say we have a 7, 8. This is a register in a computer. So these are 10 spaces in the register of a computer, and each space can contain 0 or a 1, up or down. Okay, you can put a 0 or a 1 in any one of these 10 registers. And for this, they talk about the information of the system, for which they use the letter S. Okay, and S is the number of messages, of different messages that you can make using these registers. So you could have 0, 0, 0, 0, you could have 0, 1, 0, 1, 1, 1, and so on. Obviously, the number of possible messages, which is the multiplicity of the system, is 2 to the 10th. You have 10 spaces here. So 2 to the 10th. You have 2 times 2 times 2 times 2. Or simply the number of binary numbers that you can put in 10 spaces. And the entropy, or the information, is ln log base 2 of t, which is 10. Okay, so the entropy of this system is 10, if you can put anything in any space. And the units are bits. 10 bits of information. We see now why the question is why, okay, if entropy, we're talking about entropy as being disorder, why do, T is the multiplicity, is obviously a measure of the disorder. Why not simply use T instead of S? Why put the logarithm here? Why do we need a logarithm? It's simply because we want an extensive property. If we have twice the system, we'll have twice as much entropy. Now here, if I had 20 spaces, okay, my T would be 2 to the 20th, or T squared. So it doesn't go up linearly, it goes up exponentially. Okay, but log, the multiplicity of 20 spaces would be T to the 20th, so the entropy would be 20. Okay, so the entropy of 20, of a register with 20 spaces is twice the entropy of a register with 10 spaces. That's why we do, the only reason we do the logarithm is to make it an extensive property which varies directly as the mass of the system. The natural unit for entropy then is bits, The reason we put Boltzmann's constant here is to convert from bits into joules per mole Kelvin, which I'll talk about that because we wanted. But we could talk about entropy, could be measured in bits. Okay, in that case, temperature would be joules per mole bit, which is probably the right way to measure fine temperature. Okay, but this is giving you some idea of the what entropy is. Okay, another way, because this, I talked about the entropy, and this information theory is used all the time in communication theory with the entropy of channels, the amount of information versus the amount of noise over information channels and so on. This is the unconstrained entropy when you have no constraints on the system. That is, any space could be occupied by a 0 or a 1. Now we could talk about putting constraints on the system. Any constraint is going to lower the entropy. Constraint could be, for example, we're not allowed to have more than 3 zeros in a row. Now you could work out the probability and you would end up obviously the number of microstates, the number of messages, but not permitting more than 3 zeros in a row is going to be less than 2 to the 10th. So every time you put on a constraint, the entropy gets lower. The more constraints you have, the lower the entropy, and that's essentially what a lot of this course will be. When I'm talking about solution models, the more constraints we put on the distribution of a system, the lower it's going to make the entropy. This is the highest number of messages, the highest multiplicity, the greatest amount of information, the most disorder. Let's suppose we had an extreme constraint that you were only permitted to put a 1 in every space. Okay, so the constraint is every space must contain a 1. Okay, in that case, how much information? Information is the number of messages you can convey. If you have to put a 1 in every space, you can convey no information at all, because every message is exactly the same. Okay, in that case, if there has to be a 1 in every space, there's only multiplicity is 1 and the entropy is 0. So it's the amount of information you can convey. Okay, the total number of different messages. Okay, well, every message is the same, clearly there's no entropy in the system. So in the energy level thing, when all the particles are at level 0, the disorder is 0, the system is perfectly ordered. So entropy is a measure of the disorder of the system. Now we talked about in this course, so as you heat a system up, as you take a pure material and you heat it, because of this energy level thing, the entropy goes up as you increase the temperature. So as you increase the temperature of a material, its entropy increases. We're also going to be talking in this course a great deal about the entropy of solutions, and this has to do with the so the energy levels is the distribution of particles among levels in energy space, in energy. We could also have the distribution of particles in real space. So I could imagine that I have here a lattice. These are my lattice sites in a crystalline lattice. Okay, so I can put lead and tin on these lattice sites, mixing them randomly. Let's suppose I have n atoms of tin, I have n atoms of lead, okay, and I have n total is n tin plus n lead. Okay, so now what is the entropy of distribution of the set? I'm not forgetting about energy now, but there's also a disorder because the lead and tin can be randomly distributed over the lattice sites. Now if it's a random distribution, that is an ideal solution, we assume that the lead and tin are randomly distributed over all the available sites. So the probability that there's a lead here is independent of the probability of what's beside it. In that case, the multiplicity is what? It's simply the number of ways of arranging this many tin atoms and this many lead atoms over this many sites, okay, which is n total factorial divided by n tin factorial times n lead factorial. And that's the entropy of the system, which is a gigantic number given that n total is going to be of the order of 10 to the 23rd, the Avogadro's number. But if you take the entropy as K ln T, then things get a lot smaller. Okay, so this would be the entropy of the system. Let us suppose now that we put severe constraints on the system. Let's suppose that this wasn't lead and tin, let's suppose it was sodium and chlorine. And the sodium and chlorine are now occupying a lattice site. In that case, it's almost certain that every time there's a sodium here, there has to be a chlorine here, then a sodium. And here there's going to be a chlorine, and then here a sodium. So it's going to go sodium, chlorine, sodium, chlorine, sodium. Here it's going to go chlorine, sodium, chlorine, sodium, chlorine. Okay, and now there's only one way of doing it. You put, on every other site you put sodium, and on every other site you put chlorine. In that case, the multiplicity drops immediately to 1, and the entropy is now 0. Okay, because it's perfectly ordered. This is called the configurational entropy. The configurational entropy is the entropy of distribution in space. Now, this doesn't mean that the entropy of sodium chloride is 0. At a given temperature, you still have the vibrational part of it. You still have the fact that they're distributed among the energy levels, the things are vibrating. Okay, but it means there's this 0 configurational entropy. In the lead tin solution, not only do you have the vibrational entropy due to the fact that it's not at 0 Kelvin, but you have the additional configuration entropy. So the entropy is the sum of the vibrational entropy plus the configurational entropy. In sodium chloride, it's all vibrational entropy. I'm doing this just generally now. We'll go back to this more exactly in the future. Okay, so once again, though, you can quantify things. You can actually calculate the entropy of the system as give it a number. The other thing you might notice, we'll come back to it, is that entropy can be given an absolute value, unlike the enthalpy. I said if we talk about the enthalpy or the Gibbs energy or the internal energy, the 0 is arbitrary. It's very hard to define an absolute 0 for you, exactly what is the 0 energy of the system. But you can define an absolute 0 for entropy. So entropy, unlike enthalpy, as I said, we have the convention that the enthalpy H of an element at 298 is 0, but that's strictly a convention. It's an arbitrary 0 that we set. In S, we have an absolute 0 that at 0 Kelvin, a system that's perfectly ordered at 0 Kelvin, a perfect crystal at 0 Kelvin has 0 entropy. That's called the third law of thermodynamics. Okay, so if we have a perfect crystal, meaning no defects in it, no remaining order, that's hard to obtain. If you cool a crystal down, you do have some order that's sort of retained simply because kinetically it's hard to get everything organized. But if you could get everything down to a perfect crystal with no defects of any sort, everything perfectly arranged at 0 Kelvin, you would have no configurational entropy. You would have no vibrational entropy because all the vibrators would be in their lowest energy level. The system would have a 0 entropy, absolute 0 entropy. So that's not a convention, that's an absolute thing. The enthalpy being 0 at 298 is a convention. The entropy of a perfect crystal being 0 at 0 Kelvin is not a convention. Are you happy so far? Okay. Hold on for another 5 minutes. All right. So, S can be said to be a measure of the disorder of a system. During any spontaneous process, meaning one that you observe to happen all by itself, the total entropy of the universe must increase for the simple reason that disorder is more probable than order. Okay, I gave the example here. This becomes more disordered. It's more probable that things will be disordered than they will be ordered. Okay, all the molecules up in that corner is ordered. The molecules distributed randomly over the room, that's disordered. Entropy will always increase. The total entropy of the universe will increase simply because order is less likely than disorder. So the total entropy of the universe, this is important, is that S is the entropy of the system, and S surroundings is the entropy of the surroundings, and that must be positive. If the reaction is spontaneous, that will be positive. If it's positive, the reaction is spontaneous. That is, the reaction will go all by itself, as long as there are no kinetic restraints. Now, it will go all by itself if it's permitted to. I mean, this is very simple. If I have my 2 boxes here with oxygen on this side and nitrogen on this side, and I open the hole between them, they'll mix. Okay, if I don't open the hole, they won't mix. Okay, there's a kinetic constraint. Okay, or I could put a very tiny hole and then they'll mix, but very slowly. I could put a big hole and they'll mix very quickly. Okay, the second law says nothing about the speed of the reaction, which could be 0 or it could be extremely fast. It simply says what the spontaneous direction is. If it's positive, the reaction is possible. If it's 0, the system's at equilibrium. If it's negative, the reaction will not happen. In that case, it's not a matter of probability. If it's negative, it won't happen. Okay, in other words, what that means is if I started out with the oxygen and nitrogen on both sides, and the negative, the reaction of going the other way, of them separating, would have a negative entropy. In that case, it doesn't even matter if I open the hole, it's not going to happen. Okay, so del S is positive, indicates possible if all constraints are removed on the reaction. Del S is negative is impossible, del S is 0 is equilibrium. Now, the important thing is that it's the total entropy that's important, not the entropy of the system. Okay, so for example, we observe, well, solid is clearly more ordered than a liquid. If you have a liquid below its melting point, it will solidify spontaneously, and it's becoming more ordered. So how do we square this with the fact that the total entropy has to be positive? Because clearly delta S, if I have the reaction of a liquid forms a solid, delta liquid forms solid, delta S is in fact negative. And yet, under certain conditions, we will observe that as a spontaneous process.
And there's of the system.
That's delta S of the system. It's the system that's becoming more ordered. The liquid is lining itself up into a crystalline lattice, and it's a more ordered system. Or you could do the same thing for gas goes to liquid. Clearly the delta S is negative for that reaction too, and liquid is much more ordered than the gas. Yet we observe gases condensing spontaneously. Okay, the reason being that we have to consider the surroundings. These two reactions are exothermic. Delta H for both these reactions, delta H is negative. That means if you have the system and you have the surroundings, heat is going from the system to the surroundings, and this is heating up the surroundings, making the surroundings more disordered, random disorder of motion in the surroundings. Okay, so even though delta S of the system is negative, delta S of the surroundings is positive, and if the temperature is below the melting point, the total entropy will be positive. If delta S is above the melting point, the total entropy will be negative, and it won't happen. If delta S, if the temperature is above the, we'll talk about this one. If the temperature is above the melting point, the sum will be negative, so it's impossible. You will never see a liquid going to a solid above the melting point. If delta S, if the temperature is below the melting point, okay, this will be more negative than this is positive, so you will, more positive than this is negative, so you'll have a positive total entropy. The reaction is possible. It still might not happen, because you know you can have liquids that are below the melting point in surfusion, in supercooling, because there's a nucleation problem, so it's possible. Okay, if it's equal to 0, the two are in equilibrium. It'll only be equal to 0 at the equilibrium melting point. So at 0 degrees Celsius, solid and liquid water are in equilibrium. The delta S total is equal to 0. That's chemical equilibrium. Okay, so it's the total entropy that's important. What I said, okay. Again, the second law says nothing about the rate of a process. Okay. And what I just said is written here. Okay, I'm going to take a break. The last thing, let's think about this. It should be stressed that in passing from a given initial state to a given final state, the entropy change of the system is independent of the process path, since it is a change of state property. Delta S is equal to S final minus S initial, independent of the path. Delta S surroundings, though, couldn't depend on the path. Okay, so the question was then, let's go now to classical thermodynamics. I've talked about entropy as K log T, Boltzmann's equation. But that's very useful, but I mean, only if you can measure the energy levels of the system somehow by spectroscopy can you use that. We would really like to relate entropy back to things that can be measured macroscopically in the laboratory, heat, and so on. Okay, so the next section then is to try to relate entropy as defined here to things that can be measured, okay, and make it a practical thing for doing thermodynamics. Because we would like to be able to somehow measure the entropy changes of systems. This would be extremely useful. If we could calculate the total entropy of a process, we could tell whether the process will happen or not. That's what's really, so the first law is for our heat balances, our second law is determine whether things are going to really go or not. So let's take 10 minutes and resume in 10 minutes. 20 after 2. Oh, God, stop it. Where was I? I was here? No, where was it? It was over here.
It's right here.
No. Wait, this one? No.
No, you had it just right there, where you just opened it.
Here?
You in the right corner, the small arrow. Yeah. That's in
Last one.
the last one.
Oh, here it is. Okay, great. Stop? No, that's his record.
Please.